Peraí que eu vou para aqui. Tá? So thank you for coming. I'll be talking about browser networking at dashdash, but focusing on approaches to sending events in real time to the browser, like subscriptions, which we currently do in WebSockets. And I'll show you an outline of. Okay. So I want to tell you a little bit about, just quickly, about other ways of doing subscriptions, like polling, like we'll know, and server-sent events. Then go into more depth into WebSockets, HTTP tool, also about the gRPC, which uses HTTP2 mainly to see the features that HTTP2 can give us, and then look at how Google Sheets and Excel Online handle these kind of subscriptions and what we can learn and try to improve at dashdash. And if there's time, just a quick peek at the current draft of HTTP 3. So just to contextualize, in dashdash we have, like, the most important thing is the grid of cells, and we can update cells and do some formulas and calculations. And these cells, while we are looking at them, they may change asynchronously, and we want to update the interface so the user can see the new values for cells, and they can change, like if there's the same view is open in another tab and the user changes there, then in the other tab we want to display the new cells, or because there's a scheduled process like an equals repeat that triggers a cell to be recalculated. Then if the user is in that view and the repeat triggered, we want to show the results. And this is an example of an update that I took from dashdash, and I just put here the most important fields like position and value. So this is telling us that the column, or the cell at column 1 and row 1 is now as a value ABC. So this could be done with polling, which is on the left, which is basically just making a request to the server and asking, is there any updates for me? And if there's nothing, the server says there's nothing. And if there's something, the server responds with the update. We can't be always sending these updates, these requests. So we have to define a polling interval. So let's say 10 seconds. Every 10 seconds, I ask for updates. And the problem with that is, like, we consider this delay of, if I waited here 10 seconds and there was an update here, then in theory I could have to wait up to 10 seconds to get this update, or in average, let's say 5 seconds. Then there's long polling, which tries to solve some of these problems. And in long polling, the difference is, if the server has no update, then instead of responding immediately saying there is no update, it will keep the connection open and until there is actually an update, and then only when an update happens, it will respond with that update. And then the client can immediately start another request, and which will be idle again until there is update. There's still a problem with long polling, which is if we have many updates, we have to make lots of these requests of new connections that we have to open to the server. We could try to alleviate this by maybe patching updates. Don't send the update immediately, but maybe wait for a few more so we have less requests. The problem is, of course, we get this delay again. And by the way, these images are from a book called, a free book called High Performance Browser Networking that I have a reference to in the end, so I recommend it. Okay, so that's it for polling. For server sent events, which is the image on the middle, the WebSockets on the right we'll see later. But for server sent events, the big difference is that we open only one single connection, and then the server can keep sending events back to the clients through that single connection. Let's see an example here where a GET request to some endpoint of an expects text event stream content type, and the server responds with again content type event stream, and this is the server sent event protocol. It can define first a retry, which means that if the connection is lost for some reason, the browser will wait for 15 seconds before making another request, and then it can send events. Each event can have an optional ID, an optional event type. So in this case, we have two events, one with ID 123, event type 1, and with data must be text, UTF-8 encoded. In this case, the first one is JSON, the second one is just plain text with 2 lines. And that's it. And the nice thing is that the browser handles most of the things for us. It automatically parses these events and only calls callbacks with the data. And if the connection is lost, it will retry automatically, respecting this time. And if you send IDs, the browser will automatically also send the last ID that it has seen. And so the server can send events from that ID on, so we don't lose any events. So in summary, it's simple because the browser does most things for you. It runs over standard HTTP, so you have automatic compression if the server supports it, and you can do the standard authentication through HTTP. You can choose cookies or tokens or whatever. You automatically benefit from new updates to the standard HTTP, like running over HTTP2, for example. If you're on HTTP1, each of these if you want to have various streams like this, each one has to be in a single HTTP1 request, which is a single TCP connection, one for each request. And over HTTP2, you can share the TCP connection over all of the requests, and we'll see this later. Streaming is only from server to client, so we'll see in WebSockets the client can also stream to the server, but not here. And events must be UTF-8 encoded, so no binary data, unless you want to base 64 encode it or something. So WebSockets, the main difference is that it allows also the client to stream events or requests to the server at the same time that the server streams to the client, and it's a binary protocol, different from server-side events, which is text. And so, since it's a binary protocol, it has a binary framing. So each of these, let's say, messages from server to client and client to server are composed of several of these frames. So one message can be one or more frames, and the frames each have an opcode telling like, is this a frame of data, of text, of binary data, or of text data, or is it a control frame like a ping? It has the length. The mask doesn't really interest us for here, but I can tell about it later. And then the payload, which is the message. So, like I said, there's different data frames, text and binary. The control frames close for closing a WebSocket connection, ping and pong for doing like liveness checks or calculating round trip time. At --, we don't use this mainly because, like, from the browser you can't issue a control frame. You can only do data frames, and at least from the application, from JavaScript. And we use application level keep alive in text in JSON. This is like an example of a connection in flight where the client is sending two messages to the server. At the same time, the server is sending a message and a ping. And the message one is divided in 3 frames. And what I wanted to show with this image is that, even though messages can be divided into frames, you can't interleave frames from different messages. So if this message is really long or has many frames, or has one big frame, then the second message has to wait until all these frames from the first message are delivered until it can start sending its own frames. So this means that a large message will block the other messages, and this is called head-of-line blocking. We'll see how HTTP does not suffer from this. It does suffer from it at another level, at the TCP level, but we will see that. And at --, we have to be careful with this. We have at least one big message that we send at the past cells request, which can be very big, can send like hundreds of cells, and so it might suffer from this problem of blocking other messages. This is the HTTP handshake for WebSocket. So before you can make a WebSocket connection, you have to do this HTTP handshake, where basically the browser asks for a connection upgrade to WebSocket version 13. That's a protocol of, this is in case of --, app, it's a protocol of GraphQL WS. And the browser, this was Chrome, automatically asked to use the extension of per message deflate, so compression on a per message basis. And the server accepted the upgrade and the extension. So as you can see, this is the compression had to be at the WebSocket level. It's not a normal content encoding like gzip compression. So if you want to use new types of compression or extensions, they have to be standardized at the WebSocket level, and not, you don't automatically get new things just from HTTP. So just to summarize, unlike SSE, you can have text and binary, you have full duplex streaming. There's that head-of-line blocking problem. We can, so TCP WebSockets run over HTTP1. So each WebSocket connection must use a single TCP connection. So if you want to make several, if you want to use several WebSocket connections, we are using several TCP connections. Although just last week with the release of Firefox 65, it supports this RFC, which allows to bootstrap WebSockets with HTTP2, which means that the WebSocket will run on a stream, on a single stream of HTTP2. So several WebSocket connections can be several streams of HTTP2. So only a single TCP connection. From what I found, it's experimental in Chrome. But anyway, it will be something that will give us more efficiency for free, mainly because if you have different tabs, they don't need. Right now with 2 tabs, we have 2 connections, 2 WebSocket connections, and with this we only need 1.
It won't solve the no multiply.
No. And also, this is not something for free that we get without doing anything. I will tell later, but we probably have to change the way we do load balancing. Also, it's not an HTTP protocol; it just uses it just for the handshake. So we don't get that automatically. The things that when HTTP, like when HTTP goes to HTTP2, WebSockets couldn't automatically use HTTP2. It needed this different standard just to be able to use with HTTP2. And before this standard, there were like 2 different tries to standardize a better handling of WebSockets. One for removing this head-of-line blocking, and another one for running over HTTP2 that failed the first time, and then there's this one that was accepted. So HTTP2. The main difference over HTTP1 is that it's a binary protocol and supports several streams. So here's the difference from 1 to 2, where the headers, before this was all text, now the headers go in an headers frame and the data goes in a data frame. And supporting several streams, it means that, so this is a single TCP connection, and in one stream you can make one request and get some response, and at the same time you can have here other streams making more requests, and all sharing the same connection. Let's just quickly look at the frame. We have the length of the payload, the type. We'll see there's various types of messages for data headers, flags specific to each type, and then the stream where this frame belongs. So for types, we have data and headers that we saw. This RST stream is to close a stream. Push promise is one of the most talked about, probably, about HTTP2, which allows the server to like, if it receives a request to index HTML, then it can tell the browser, well, you probably want is something .css or this JavaScript, and it gives like the headers immediately for that, and then if the browser doesn't say anything but like refusing that, then it sends the data for that, so the browser doesn't even have to ask, and then the browser can cache that and use it when it needs it, and there's a ping as well. So this here is a connection like we saw for WebSockets. We can see here that since we have this concept of streams, we can interleave frames from different streams, and the server will know how to put them all back together. So we don't have that problem of head-of-line blocking at this level. So if stream 5 is very big, we can keep sending stream 3 in the middle. There is offline blocking, but at the TCP level. So this here is a TCP connection, and let's say that each of these frames goes in a TCP packet. And if, let's say, this one is lost, then and these are received, then the TCP layer can't deliver this to the application layer, because since it does not have this concept of streams, it only knows for TCP this is a single stream. So it will have to wait until this is redelivered, and so it can deliver these and then the others. And so actually, if there were some studies done, and if the loss, the packet loss in a link is more than 2%, then it's the performance of HTTP 2 will probably be worse than HTTP 1, because with HTTP 1 you open like up to 6 connections at the same time. So if one loses, the others can continue. But in HTTP you only open one and send everything through streams, and with that kind of loss, everything just gets worse. And we'll see that HTTP 3 will probably solve this. So gRPC, I want to talk about it because it's an interesting way to see how all the features of HTTP 2 can be used by a communication protocol, besides normal browser request response. So gRPC allows for 4 method types. Unary is basically just a normal request response. Server streaming is request, and then the server can keep sending events to the client. Client streaming is the other way around. And bidirectional is like we saw with WebSockets, is the client can keep sending things to the server, and the server keeps sending things back. All of these requests, if you make several requests, all of them will share the same HTTP2 connection, each one in a stream. This is an example of a unary call. So it's the request is an HTTP2 request with some headers. So it's just a normal HTTP request. It's opposed to some path. And then after the headers, the data of the request. And the response, it's again a normal response with data. And the difference is at the end, there's another headers frame, which gRPC calls trailers, with specific data specific to gRPC protocol, like the status, the errors, and trace information. And that's it. gRPC web. The interesting thing about this is that even though gRPC, the normal gRPC, runs over HTTP2, you can just use it from the browser and talk to a gRPC server. A new protocol called gRPC web actually had to be developed. And this is interesting to know because for the same reason, we can't, even though HTTP2 is in every way improves upon WebSockets, you still need WebSockets for some use cases like bidirectional streaming. So let's look at gRPC web and then talk a bit more about that. So gRPC web has to run over HTTP 1 and 2. Since you can't directly send headers, you can just from the browser say, I want to send this request with this data. You can specifically send the HTTP2 frames, so you can also read them directly. So you can have a different header for these trailers. It goes in the response body. They default to encoding protobuf. So I didn't mention, but gRPC uses by default an encoding called protobuf, which is a binary representation of some structures that you can define. And for gRPC Web, they default to text because they say that the binary encoding is not the most CPU efficient for browsers, and that's the generated code for parsing the binary it can get very big if you have a big schema, so probably get a very big JavaScript file. Because the protocol is different, you have to have a proxy to translate between gRPC Web and gRPC in normal gRPC. And there's no support for bidirectional streaming and client streaming. And at least over HTTP 2. And they say that there will probably be that support when this standard called portability streams is implemented in browsers. Until then, there's experimental support for bidirectional streaming by using WebSockets. So, in summary, the first points tell us that HTTP2 is like, it seems at first like WebSockets, but better. So text and binary, full duplex, stream multiplexing, so no head offline blocking. We only need one TCP connection per origin. So you make, even if you have several tabs open to the same origin, you only need one HTTP connection. There's still that head offline blocking problem, but if you have use cases like bidirectional streaming, then you can directly use HTTP2 for that.
Do you think that the proxy that does the translation between gRPC Web and gRPC brings latency to the call, or does it have any impact? Or
the proxy can be directly in the application of. So let's say you have the server written in Java, and the proxy can be in the same Java application, so like another port. So it doesn't need to necessarily add that much latency. Probably the text, like if you're using protobuf text, it can at a server side be less efficient to decode it or something, but in theory you don't need to have a big hit in latency. So that's it for HTTP2. So I went and looked at how Google Sheets handles subscriptions, and they do something very similar to server-sent events, but in a custom protocol. So instead of that text that we saw earlier, they send something like this. So they send a GET request to this --bind path. Then the server responds with content type text plain, so not the text event stream that server sent events uses. And it keeps the connection open and sends these events through the connection. So here there's 3 events. 2 actually are no ops. They're probably like keep alive. This is over 60 seconds. After 60 seconds, they close the connection and make a new one. So this is probably some keep alives and sorry. And this I'm not sure what it is. I must have been moving the mouse or something on the other browser, and this sent some event. For Excel Online, they use WebSockets with I call it minified JSON, but just because they try to make messages very small, so they use JSON in WebSockets, but they call their attributes just like one letter long, and they try to they use this encoding for events like that to make it as small as possible. They also don't send all the data through WebSockets. So if the data is small, they send it. So if I change my selection, so I'm selecting cell A1 and now select cell A2, they send that to the other client that I'm selecting cell A2. But if I change or if I mutate a cell, they don't send the whole cell mutation. They just send to the client. There was a mutation on cell A2 or on cells like A1 to B2, and the client receives that notification and then makes a new GET request and asks for the changes in that range. So they try to use WebSockets only for very small messages and for notifications only. And actually, they only open a WebSocket connection if there are more than 2 clients on the same spreadsheet. So if you are the only one in the spreadsheet, there is no WebSocket open. And to know if another client has arrived, they use normal polling. So like every 5 seconds, they do a normal poll to get the status, and if there's another user in the meanwhile, if it arrives in the meanwhile, then they open a WebSocket connection. So with this, we can have some ideas for potential improvements that probably most of these are not very or can wait for later until they are until we have more scale, or probably they are not a problem for now, but you can think about them and see what we can do. So like Excel does, we can, right now we are using, every operation is through WebSockets, be it big or small, and you probably want to move some operations outside to normal HTTP. Well, past cells is probably the biggest one, which can have which can become very big. We can try to use a smaller JSON encoding. Actually, before one of the ideas that I had was actually using like a binary encoding, like protobuf. But as we saw with gRPC Web, they even don't default to the binary encoding because of the primitives that you have in the browser to handle binary data and to parse it are not as efficient as possible. So probably text is better for now. We could try sharing WebSocket connections between tabs. So if we have that RFC that I spoke earlier available that runs WebSockets over HTTP2, that would help. There's also another way, even without that. Pusher published this blog post talking about a way of using shared workers. Like the first tab creates a worker, and the worker creates the WebSocket connection, and then all the tabs just make requests to that worker, and the worker makes requests on behalf of all the tabs, and then sends the responses to the correct tab. That's to keep track of which tab wants what, but then you only has one WebSocket connection. Right now, we are using, in front of our WebSocket server, we are using an SSL load balancer, and because at the time it was the only load balancer that you could that could support WebSockets. Sorry.
Mas posso continuar.
English.
So we are having technical difficulties. And we'll be back in 1 minute. Não durou nada, pá. Eu desliguei da ficha tipo, antes de estar aqui, às 4. Se tivesse João Marcos, não acontecia. Apareceu ali as bolinhas. Depois aqui estava sininha, mas não apareceu as bolinhas. Okay, so I was.
Tenho certeza. Como é que eu saio?
Faz share agora, like that?
A máquina vai ser antes das 6.
Pois aí, os conectos de um guest.
Já está? Okay. So, SSL load balancer. At the time, it was the only load balancer that supported WebSockets. The HTTPS one did not, and now it does. And one of the benefits of the HTTPS load balancer is that it is generally better supported by Google. Like, it has new features sooner than the Cloud Armor, which like their DDoS protection and several things more available sooner. It also the other big advantage is that the SSL load balancer will probably never support that RFC that I talked earlier of running WebSockets over HTTP2 because to do that you have to negotiate HTTP2 at the SSL level, and the SSL load balancer does not know anything about HTTP basically. For that you need the HTTP as load balancer. And with that, it's in theory possible to use that RFC feature, but we have to try and see. So, so one basically just pay attention to these new developments, like gRPC web. I'm not saying to use that, but the issues that they're facing and they're solving with running protocols over HTTP2 on the browser, it will probably be something that can help us as well understand what we can do better and what we have available to use on the browser as well, instead of besides WebSockets. So HTTP 3, it's currently in draft. It's likely that it will be standardized. It's not 100% certain, but the current draft is based on Quick, which is a protocol developed at Google. And basically, Quick is an alternative to TCP. So it's also a transport level protocol with congestion control, loss recovery. The big difference is that it knows or has native support for streams, for multiple streams. For TCP only knows about one stream, and Quick has this concept of streams, so you can map the HTTP level streams to the Quick streams, and with that you avoid that head offline blocking that I talked about that we have at HTTP2. Also, it has faster connection setups. It can even in some cases do basically no connection setup, is 0 RTT. It's basically on the first packet you can already send data if you have if the client already had a previous connection to the server, it can use the secret key negotiated on that previous connection and encrypt already the first data packet with that, and so you don't pay for any handshake. And it will probably have a few more things before it's standardized, like better support for things like switching networks, like switching from Wi-Fi to 3G or something. But for now, I think these are the big ones. And that's what I had to say. Here's the book that I mentioned, where most of the pictures were from, and I recommend that you check it out. But that's
One quick question. So I don't know really a lot about HTTP3, but do you feel that moving from TCP to UDP and developing the TCP-like stuff for loss for recovery and congestion control is the right move, just to get the streams for free, or do you feel that HTTP could combine both TCP and UDP and maintain the true semantics for the connection?
What do you say that could combine both?
Yeah.
The TCP?
So HTTP3, it moves to UDP and has some extra layer on it to basically mimic TCP. It could use both TCP and UDP, one for streams and another one for quick request response semantics that we already have. Do you think that it could be better, or do you think the current approach could be better for the current problems? Do you think that we are going to create other problems with that?
And by the way, another alternative would be to, instead of basing quick on top of UDP, you could do it directly over IP, for instance, and like do this at the kernel level, because right now you implement quick at the user space level, and I think that's one of the big reasons why they went with UDP, is that you can, it's just much more quickly to develop new protocols if you do it over one of these that are implemented in the kernel, but then you can develop your own protocol in user space that you implemented in the kernel, and also most of the middle boxes on the internet, we will only know these two. So again, TCP would also work for that. I don't know, maybe if you're saying using both, probably that was maybe complicated. But I can't really tell you. Yeah.
Oh, thanks.
Also, just a question, like gRPC web is fully supported by all browsers or just a subset?
Good question. There are at least two big implementations. Let me see if let's see. I think at least the most used ones are certainly supported. But do you have a specific reason for asking, or a specific browser?
Just Chrome and Mozilla.
Those are certainly supported, and Safari. But let's quickly.
Chrome being Google, most certainly supported.
Oh yeah, but you would think that, but sometimes Google products don't really. I mean, they launched gRPC a long time ago, gRPC web, and their spreadsheet application is still based on the same steps. So.
Maybe it's very sensitive.
Yeah, maybe it is.
I can quickly find out, but I'm pretty sure.
I mean, it's just,
It was actually developed at Google and at Improbable at the same time. They were, without knowing, they were both developing kind of the same thing, of the same idea. And then when they find out, they decided to join efforts. But yeah, I can't really. But I remember when the news came, like a few months ago. I think I remember that it was pretty good supported. But I don't really look at least I don't look much at the browser. I just look. Does it work in Firefox?
makes sense. Also, you mentioned a very interesting thing which is it's more efficient to be encoded as text instead of binary. That protocol. Do they mention like possibilities of doing a text encoding inside the message, or that's probably overkill?
That's what they're doing, a text encoding of the protobuf.
Okay.
Like it's probably like when you print a protobuf in that short form. Maybe I didn't look at what it looks like, the text form, but let's say it's something like that. It could also be JSON, but I don't think it is. I think they have there's a different encoding for that. So this text one is called gRPC-text. There's one just called gRPC, or just called gRPC web, and one gRPC web text. And there's another one that's called like gRPC something JSON. And so I think this one is one that was made specifically for being fast too.
And the JSON will be more like friendly to some level.
Yeah,
Yes.
Because browsers don't natively decode and encode photo.
So
Maybe if they did, the overhead would be simpler.
yeah, you have to give them like the schema, because each application has its own schema. But yeah, the main problem is that from what I say, that the primitives that you have in the browser to decode and encode binary are not very efficient. And also you have the code, the code size, like the code size in JavaScript to do that. That gets pretty big. Yeah. Okay. So thank you again for coming. I'll close the stream now.